Right, let's settle down. I know it's hard to come back in from that beautiful sunshine class, but that's what you're paid for, so let's move on. So what I want to do now is continue on. Now that we have some of the basics, I'll speed up a little bit for the second part here. I won't go dwell into as much detail, but I want to hit the high points for a number of things that are really important going forward and setting us up for this afternoon with our interferometry introduction. So I mentioned polarization, and I mentioned that different transmit polarizations behave a little bit differently. So this is a very famous radar image. It gets shown zillions of times. It's in many books that talk about radar. This is an image of San Francisco. For those of you who don't know San Francisco very well, it's about 500 kilometers north of here. This is the Golden Gate Bridge, whom I'm sure most of you have heard about. And then this is the city itself right here. There's a park, very famous park in the middle of the city called Golden Gate Park. That's the Golden Gate Park right there. And then this is the ocean that you can see out here. And then this is different polarizations, transmit and receive combinations that have been looked at. So for instance, this is transmit horizontal, transmit receive. This is vertical. This is transmit horizontal, receive vertical. There's different combinations, polarizations here. You'll notice the city looks very different at the different polarizations. So indeed, the different polarizations are sensitive to different aspects of what's on the surface, and that's why it can be very valuable in terms of looking at things. Just to point out a couple things. So if you look at Golden Gate Park, you can see some places where the contrast between the park and the city is very high. For instance, here. And then you can see some places where the park practically disappears. For instance, here, in transmit horizontal, receive vertical. And you can look at the ocean, look how dark it is in some images, for instance, here, and look how bright it is compared to the rest of the background of the city here. So depending on what you're trying to look at, different polarization combinations can be extremely useful. Another example of polarization exploitations in a planetary mission is there is a mission to the moon, and in the south portion of the moon, there are craters that are permanently shadowed, meaning they never get any sunshine. And why do people care about that? Well, people believe that over time, that ice from comets or whatever got trapped in the bottom of those craters, and since they never see any sunshine, they can persist on the moon for a very long period of time. And in fact, it has been detected in those shadow craters. And by using circular polarization ratios, that's one of the ways they detected it. They were able to detect buried ice in those permanently shadowed regions on the moon. So polarization information can be very valuable for a number of different applications. So can anybody tell you, why do I care about water on the moon?
I don't care about Mars.
What? There's a lot of people who care about Mars, but I'm asking about the moon. Well, as many of you know, or have read in the newspaper, at least the United States and China are both planning to go to the moon here within the next decade. And if you want to have a permanent presence on the moon, what do you need? Well, you need some form of power, and you need some way of drinking. For instance, if you're human, for instance, bullets don't need so much. And that's why I prefer robotic explorations. But if you want to put humans there, it turns out that one of the places they're planning on putting a permanent base is in the South Polar region. And they want to be able basically to exploit water in these regions to relieve the need of carrying water to the moon. The cost of launch depends on how much mass, how much you want to put into orbit. And the more you want to put, the more expensive it is. And water is heavy. You want to take a lot of water to the moon, you're going to pay big bucks to do that. So if you can find it there, it saves you a lot in terms of your mission resources. So that's why the people care about it. So the projected, how much area that you're getting on a ground resolution element depends on the local slope that you're getting back toward the radar within a range resolution element. So remember we said the world is going to be divided up into range bins or range distances separated by between one and another, say delta rho, well, that should be the size of the range resolution element. And how much area that represents on the ground will depend upon the local incidence angle. And so the formulas here relating this area that you're going to get on the ground and the incidence angle are given by these formulas. So tau sub rho here is going to be the slope in the cross-track direction. So if I'm looking this way and I have a slope that's facing toward the radar, that will be a positive slope. And if I have a slope facing away from the radar, that'll be a negative slope. That's the sign convention. So if I'm pointing toward the direction of the radar, it's positive. If I'm pointing away from the radar, it's negative. And what you see then is that the area, the delta S will be the resolution in the along track direction. But the ground resolution that I get in the cross track direction will depend upon the range resolution and the local incidence angle, which will depend upon the look angle, theta L, and the slope. So the steeper the slope is, then that will change this projected area. Now, something funny about this formula. Somebody tell me what it is. So I'm saying that my delta G is going to be a function of delta rho, and it's going to be divided by this quantity here. The sine of the look angle here and the slope.
Is there perpendicular? The sine is going to become 0.
Yes. So if the look angle equals to the slope,
Yeah.
this is 0. And that means the projected area would become infinity. Is that a problem? No opinions? Are you, come on. Is infinity going to be a problem for us? Yes, there are no projected areas that are infinity. So obviously this formula is an approximation. So this is something to be very careful of. You'll see this formula in zillions of books. It's not exact. It is an approximation, and it's very good most of the time. But when these two angles get too close to each other, it's not the right formula anymore. And there are a lot of formulas, some for interferometry, some in radar, where you see equals in books. But if you're not very careful, they're often just really approximations. Sometimes the author's very careful about saying this formula is only valid when, and sometimes they're not. So something to be really careful of, particularly for those of you who are doing your own research. Yes, it's fine to look at papers, and yes, it's fine to look at books, but if you're exploring a new area yourself that hasn't been very done, and you're not just exactly copying well-trodden algorithm, you're trying to develop something new, you better make sure you understand the things that, the formulas, the approximations that were used, that you're not starting off on the wrong basis and then getting a wrong answer because of that. I've caught a number of students that got caught in this thing. They came to me and said, I'm having a problem, I can't figure this out. And then I had to go very carefully through things, and then I finally find, oh, at this point you assume this, and this is not true for you, because what you're doing is different. So you need to be careful. For those of you who are out there that are starting your own research, you need to understand the basis under which your work is being based, right? So be very careful about that. I have a problem related to that in here, which is this exercise right here, which I won't go into. So backscatter, which I just mentioned, turns out, as remember, is related intrinsically to what's on the surface, but it also depends very much, it's very angular dependent. It depends very much on the incidence angle, and that's why incidence angle is really, really important and why we care about it in terms of understanding how much signal we're going to get back from a radar. And typically, it has a behavior that for 0 degree incidence angle, meaning I'm looking perpendicular to the object, so either straight down or the surface is perpendicular to the direction I'm looking, then I'll have a very high backscatter. And as I go more and more away from the incidence angle gets larger and larger, my backscatter drops down. And it makes sense, because at 90 degrees, it means I'm looking right along parallel to the surface, so I don't get anything to reflect from it. So at 90 degrees, it typically will drop off to 0 someplace over here. So there's a lot of things that affect backscatter. There's no one backscatter curve that works for everything. So life is complicated. And sometimes you can write your theoretical ways of deriving these formulas, and oftentimes you can only get an approximations with the theory, and you have to go out and measure it in the field. And you have to get an empirically determined backscatter curve. What affects this? Well, there's two primary physical things that are affecting what's going on. There's the so-called dielectric constant. That's a number that's related physically to what the material is made of electrically, how it looks electrically. So it determines how much reflected signal comes back from that surface. There's actually two parts to the dielectric constant. Sometimes we call it the real and imaginary part, or the complex dielectric constant. So the first part of it determines the reflection. The second part of it determines how much penetration you get, how much will you be penetrating into a volume, how much you're penetrating into the ice or the soil or whatever. So this number here, and it's sometimes there's other ways of parameterizing it. Sometimes people do it in terms of the loss tangent or whatever, but there's two numbers basically. One determines reflection and the other determines penetration or absorption into the surface. It also depends upon the surface roughness. And this is another key thing. Roughness matters at the wavelength scale. So it's not that you can just make an absolute measure of the roughness and know everything. So something that's, say, suppose that you're measuring something with a 1 meter wavelength thing. The wiggles that are, say, a half a centimeter, they don't matter too much. They're not very big relative to the wavelength. So the radar at that wavelength doesn't care about it, quote unquote. But if I measure this with a 3 centimeter wavelength with a half meter bump, well, half centimeter relative to 3 centimeters, that's pretty big. So it's going to care. So it's wavelength, it's roughness at the wavelength scale that matters. Okay. So unfortunately, we always seem to report roughness in terms of an absolute quantity. It's 3 RMS, root mean square, centimeters squared or whatever. But if you really want to translate it into something useful for scattering, you should convert it into something in terms of the wavelength you're going to be imaging it at, because that's going to tell you how much impact it's going to have. So you need to think about it in terms of wavelengths. So the things that it also depends upon: surface wetness, soil moisture. So like I said before, something you can care about. Vegetation level, how much biomass is there? This is one of the ways we try to measure biomass. How much there is through the backscatter levels. Urban structures, if you put buildings on there, that matters. How the buildings are shaped, how they're oriented relative to the radar, that matters. If you're looking at the ocean, the wind speed, like for a scatterometer, it matters. So it all depends on what you're looking at and what wavelength you're looking at. So I can't give you one general rule that says, this is how the backscatter behaves. It's much more complicated and nuanced than that. But these are the general features that you have for a backscatter curve.
So, one question. So here, like, the topography doesn't count.
What?
The topography, I mean.
Topography does count. Everything counts. So topography plays a role, but and it depends on the scale of the topography. So let's suppose I have a surface slope here, like this. So, and then on top of that, I have some sort of modulation. So it depends on what you mean by topography. So topography can include anything from measuring things at meter scales or tens of meter scale, like a typical topographic map, or you could give me microtopography, measuring things at the centimeter scale. Well, let's take a typical radar resolution element, say meters to 10 meters, just for the sake of argument. Well, the microtopography here, it's going on within my, say, my X meter resolution cell. That's going to affect the surface roughness. And so it's going to impact through the backscatter. However, the tilt affects what we were calling our A sub G, our area in the cross-track direction. And that was our delta rho divided by sine theta L minus tau sub rho. This is our tau sub rho. So this gets scaled by the slope of the local topography. So as I get more normal to the angle of incidence, I'm going to get something brighter in my radar image, but that's coming from the macroscopic topography relative to the pixel size. So both effects are there. One of it, though, is an area term, which if I have a good topographic map, I might be able to subtract out or normalize out of the data and get back to something that doesn't depend upon this, which is what I want to do in many cases. But the signal that I originally get will depend upon this, and if I want to try to get to something that's, say, only dependent upon this roughness, I'm going to have to take this part out. Okay, and then for that, I need information about the topography to do that, because I need to figure out what the slope is. Okay, does that answer your question?
Yeah.
Yes.
I think frequency can affect the backscattering also.
Yes, well, frequency is wavelengths. That does it, and that is because, again, the roughness and the dielectric, how much the reflectivity and how rough the surface looks like depends upon the wavelength. Both do. So the dielectric and the roughness are both depend upon this. Okay. Now, the actual physical roughness, RMS, doesn't depend, but the roughness that matters is the relative wavelengths. Measured roughness. What?
How does the wind speed impact this?
Because what the wind speed does is when wind blows over the surface of a water wave, it changes the shape of the little ripples on the top of the surface. So it basically changes the roughness of the surface. And the higher the wind speed is, the more roughness that you get on the modulating the wave, and therefore it shows up in the backscatter.
Okay, so it's not directly from the wind, it's what the wind affects.
It's what the wind does to it, yes. Yes, it's not because the wind is blowing, the radar doesn't care about the air per
Right,
se.
that's
It's what it does to the water that it cares about. This is an example of a backscatter curve that we used in Venus for Magellan. And again, you can see the general shape here of what the signal looks like. And here, these parameters were determined empirically, so for the particular surface. So sometimes there's nice analytic forms that we use. Sometimes there's just apply. Okay, so this is the surface of Venus. This is what it looks like at two different frequencies, S-band and X-band, which are two frequencies we are looking at going back to the moon, to Venus with imaging. So you can see how the backscatter varies over the entire surface. So in this case, the range of backscatter varies is about 10 dB over there. Well, it's actually a little bit more, but the bulk of it's within 10 dB over the surface. Okay. So different surfaces reflect things differently, as we sort of getting at. So if you have a very smooth surface, it acts like a mirror. So just 1 second.
So there's no refraction happening?
Refraction happens in the air, and yes, it does happen. It's a property of the medium. It's relatively small for microwaves in the Earth. In Venus, it turns out to be a big deal. On the Earth, it's not because of the way the atmosphere is. And so when a wave hits a very smooth surface relative to the wavelength, it looks like a mirror. It tends to reflect off, and it looks very dark. So if you see roads, oftentimes in radar images, they'll look dark relative to the background because they're basically mirrors to the incoming waves. If you have different crop surfaces, they will look differentially rough, and the different plants will have different different dielectric constants, and so they'll reflect things differently. So you can see different patterns coming from the different crops, coming from their different surface roughnesses and dielectric patterns. Sometimes you'll see regular patterns if you have a series of crops, and sometimes things that look a little bit more irregular. Mountains have a lot of slopes in them, a lot of slope variation, and that slope variation shows up very strongly in the radar imagery. You get a lot of bright things on slopes facing right back toward the radar. You can have radar shadow regions that are blocked because they're occluded by the mountains, and so you get dark areas that are due to radar shadow. Forests are very, very complicated to be. So whether you're looking at a boreal forest, or you're looking at a tropical forest, or a temperate forest, they all look different. They all behave differently. But they tend to scatter higher power levels, and they tend to be a little bit brighter and show some interesting textures depending upon what the vegetation cover is. One of the most complicated environments is an urban environment. There's just a lot of multiple reflections off buildings, surfaces, and grounds. And depending upon the resolution that you're looking at, things can look very different and very complicated in an urban environment. Another thing about wavelength is different wavelengths penetrate differently into surfaces. The general rule of thumb, remember this, longer wavelengths tend to penetrate more deeply. Not always, tend to penetrate more deeply. So if you come back and say, Scott said that this is true, I will deny saying that. But what is true is, generally speaking, the longer the wavelength, the more penetration you get into different surfaces. So whether it's a forest, a dry soil, or an ice surface, longer wavelengths will tend to penetrate deeply, more deeply into that surface. So L, C, and X band, I showed you 3 different wavelengths here. You've got different levels of penetration into those surfaces. And therefore, wavelength selection matters depending on what you're trying to do. So if you want to measure the top of vegetation, then you want a shorter wavelength. If you want to try to understand what's happening at the base of the vegetation, you're going to want a longer wavelength in general. So there's an example of actual imagery. X, 3 centimeters, L band, 24 centimeters, P band, 80 centimeters, roughly speaking. So 3 areas imaging the exact same area in roughly the same time. And this is what the imagery looks like. Notice the difference between them. So let's think of a couple of areas and see if we can understand something about it. So let's look at this area right here. So this is X band, and this is a suburban area, okay? And what do we see here? So this is X, L, and P. Well, the X band looks sort of more uniformly gray compared to the other 2. The L band, we seem to get more separation here between the various building structures and the roads. And the P band looks like we get dark areas, really bright areas in the urban areas, but we still get sort of reasonably good road separations. Somebody want to tell me? Somebody give me an explanation of why it looks the way it does. Why do I see the relative differences I'm seeing there? What do you think is causing the difference? Or what do you think are some of the causes, at least, that are resulting in the differences here?
Penetration.
Okay. I heard some of the answers that I care about, but one at a time now. I heard somebody back here. Yes.
Penetrations of waves are different. So
Penetration into what?
X is more of surface, so we are seeing grayish of all types of regions in those.
Well, what do you think is in the sea that's penetrating differently in?
On the surface, we are
What surface of what? Composed of what?
buildings and roads, everything. We are looking at the top of.
Not quite, but you were, yes,
Maybe there are trees on streets.
there you go. Vegetation. So in the neighborhood I live in, we have trees. Maybe not you, but in my neighborhood, we have trees. If you're in Arizona, maybe no trees, but for the rest of us. Okay, so, and here, this is a typical urban area, and there are a lot of trees. So here we're having some sort of vegetated area around there. We're getting kind of bright surface scattering because it's kind of rough at L band. And we're not seeing the road so well, and we're seeing kind of some blurring because probably we're not penetrating the trees around the houses very well. Then we go to L band. So L band says, I don't care about those trees as much. So we're getting more penetration in there. We're getting more delineation between the local structures in there. But we still see some bright areas in the surrounding areas, except for this field right here looks relatively dark. So this might be sort of a bushy area, but looks sort of smooth at L band, but bright at X band. And then we get to P band. P band penetrates really deeply, but now what we're seeing is we can see all the corner reflections. We're getting a lot of double bounce from there. So we're getting a lot of direct interaction of the ground surface, which we didn't penetrate all the way to the ground at L band. So it looks very bright around the buildings. All the vegetated areas around there look dark. And so that's what we get. So the scene's the same, but it looks very, very different at the different frequencies. you can look at different areas. For instance, this area up here, which has a lot of low-level vegetation, you see it looks very bright at X band, a little bit darker at L band, and basically uniform at P band. And you can go through and look at all the different elements in there. So understanding knowing the wavelength is absolutely essential to interpreting radar imagery. Okay? You have to know the wavelength.
I have a question.
Yes.
So, on the previous slide, so below that water body, you see two dots in X band, but it's not visible in either L or P bands. What are those?
I have probably, if I can figure out what specific dots.
So,
This body here,
yeah, and below that is,
Yeah.
you mean those two dots?
yeah, those are not in any other.
Don't know. I don't know. That's a quick answer and the right answer for me. Okay, somebody had asked, well, how do I separate surface roughness from, for instance, soil moisture? Well, that's really complicated in general. I will tell you one of the simplest models and that has worked under simple situations. One model that's out there is called the small perturbation model. And it's a backscattering model that's related on knowing something about assumption about the surface roughness. It's valid when the surface roughness is relatively small, works for light vegetation. And basically, what you find, if you work out the formulas, this is a case where you can do things analytically. You can work out what the backscatter is at HH means transmit H and receive H, and VV means transmit V and receive V. And you can find out that the backscatter is related to K and H are parameters are related to the surface roughness, okay? As is a W. So these things are related to the surface roughness. And the alpha is a parameter that's related to the dielectric property. And the dielectric is related to soil moisture. So it's this little chain of events. So what the good news is here is what you see is this backscatter level here is dependent upon the roughness and the dielectric, which depends on the moisture. And then if you look at the formulas, you see that all the roughness parameters are the same for HH and VV, and the parameter that will be different is alpha. And this is what alpha looks like. So alpha depends upon the dielectric and on the incidence angle. So if I take the ratio of sigma HH to sigma VV, all this other junk that I don't want cancels out. And I'm left with alpha XX and alpha VV, which has just the dielectric property and an angle. And then if I know a formula that relates the dielectric to soil moisture, I'm all done. So that's the way that these things typically work. I have to chain things together. I have to cancel out the things I don't want using some sort of knowledge about the theory or something determined empirically, get rid of it, and then I can estimate the parameter I want. And this is a very simple example, but it's illustrative of a general way of approaching a problem. Yes, in the back.
Yeah, sorry if you reviewed this before, but the H and the V, what are those defined in respect to?
So
What is considered H and V?
H and V are referred to the horizontal and vertical polarization, and they're referred to their reference relative to the direction of propagation. So I won't go into the exact definitions because it'll just take me a little bit of time to go through it. But basically, think of H as horizontal and V as vertical. That will work for today. Any other questions? Yes, way in the back.
In case of vegetation, does the same polarizations affect like structure and moisture, for example, or is it different?
So it will. So the question is suppose suppose you're measuring moist vegetation. Does the moisture in the vegetation and the structure of the vegetation, is it reflected the same in H and V polarization? And the answer is no. Usually there's a difference between how this moisture and this vegetation structure interact with the content of the moisture in the vegetation. And that allows you to try to work on separating these things. So so there's the formula. It turns out there are formulas that relate, that depend upon the soil type and the amount of soil moisture you can relate to the dielectric. There's one version of the formula that's out there for doing that. There's many more out there and more complicated formulations that are there. This is just one that was used a long time ago, not so much these days, but it's simple to explain. And so then you can see how the dielectric depends upon the amount of soil moisture. So 0 means there's no moisture in there, and this is the volumetric soil moisture, but it's the soil moisture by volume. And you can see that the real part of the dielectric goes way up as the soil moisture goes up. So you can see there's a way to invert that information. And that's what people look at when they're trying to understand that. And that's for a particular soil type. So there's another piece of information. Now, people are doing global retrievals of soil moisture these days. And of course, they don't know the soil type for every little dinky spot of point on the ground. So they work on these more generic formulas, but they are scattering specific. They use these big scattering models and invert from cubes where they try to use various parameters to estimate things. So life can get very complicated in the real world. But the basic idea is, and the underlying physics is basically the same. All right, now we're going to get to one of the key equations of understanding what we get back from a radar and how much signal we get back compared to the amount of noise we get back. So this is called the radar range equation, or the radar equation for short. Okay, and by the way, this equation will make an appearance in your quiz this afternoon, so you may want to pay attention to this. Okay. Now, you don't need to memorize the equation, but what you should understand is the sensitivities. That's what it depends upon. And so SNR, first of all, is the ratio of the amount of signal you're getting back to the amount of noise. All measurement systems have noise in them, unfortunately, but that's just the fact of life. And in radar, the noise is related to what's called the background thermal noise. There's other types of noise we'll talk about in a little bit, but thermal noise is the one we're going to be talking about. And thermal noise is basically a result of the fact that things have a temperature. Electrons move when you're above absolute zero, which means that noise gets created or signal gets created at RF frequencies because of that. So there's a natural radiation that occurs as the temperature gets higher, the electrons remove more, and there's more signal energy that's generated that competes with our CERN. And the amount of noise that you get is this formula, KTV. And this is really important formula. So K is a constant, it's called Boltzmann's constant, and it's written down here just for reference. T is the system temperature, and B is the bandwidth. We're going to learn more about bandwidth coming up, but bandwidth is related to the range resolution. And this is what becomes one of the key traits in a radar. If I want more range resolution, I want more bandwidth. And this is easy to understand. When you're at home and you have a Wi-Fi system, you're on the internet and you're using your Wi-Fi, what do you want? You want more bandwidth. The higher the bandwidth, the more data you can exchange, the more information there is. Well, the same is true for a radar. The more bandwidth you have, the more resolution, the more information you can get. That's how you remember it, okay? It's really simple. So if you're saying, I want more resolution, I want a half meter, or I want a quarter meter, whatever it is, you need more bandwidth. And that sounds all fine and good. But as soon as you say you want more bandwidth, you get something else you don't want. You get more noise. So nothing's for free. So there you go again. So you want resolution, you get more noise. And that means you need more signal in order to extract what you're looking for. More power, more something, more gain in the antenna, whatever, in order to overcome that. So you always have to balance between how much resolution you really need, because that determines your bandwidth, and then that determines a lot of other parameters about your system to overcome the noise. Okay, so SNR is one of the metrics that we care about in terms of understanding how well our system will be. And the equation that we use to do that is the so-called radar equation here, which tells us what the SNR is related to. And there's a couple of, we can just sort of follow the transmit and receive change to see the basic idea of where the formula comes from. I won't derive it in detail, but I do want you to understand the sensitivities here because it's a little bit important. Okay, so not surprisingly, the amount of transmit power you have affects your signal to noise, because that's going to affect how much signal you get. The more power, the more signal you're going to get back. So that's P sub T. The next thing that affects it is the gain. So how much peak gain you have. So the more gain that you can get in your antenna, the better off you are. So on your transmit, you're going to transmit a gain. Remember, I showed you that formula is related to the antenna area and the wavelength. Then your signal is going to propagate out. And so basically, your signal starts out as a dot transmitting from your antenna, and it transmits and it propagates at any one time. It will go a certain distance, r. And what is the shape of an object at a fixed distance from a given point? What's the shape? If I'm at a fixed distance from this point in three-dimensional space, what do I get? A sphere, a ball. So the energy, it would expand out on a ball. So, and how many people remember what the area of a sphere is? One person? 4 pi r squared. So that's where the 4 pi r squared is. So the energy starts out and it gets diluted by 4 pi r squared. It's like it gets smushed out onto a sphere. Then I hit the ground, and as we learned before, the radar cross section is going to be the backscatter times the area. So I'm going to get back, I'm going to reflect back something that will be proportional to that. And now I'm going to go back to the receiver. But now, here's my pixel on the ground. Now this radiates back toward my antenna. So again, my signal from that pixel expands out on the sphere again. So I get another 4 pi over r squared on my way back. Then I get the gain of the antenna. My receive gain can be different than my transmit gain. Don't worry about that, but it can be different. And then I get various losses. I can get losses from the atmosphere, losses in the electronics, et cetera. So I have various losses that yield my total losses here. And so my signal to noise then will depend upon my buildup of all those various things. So it depends upon, it's proportional to the transmit power, it's proportional to the antenna gains, it's proportional to the backscatter, and it's inversely proportional to the losses, the range to the fourth power. Very important. You get and then of course, the amount of noise, which is proportional to the system temperature and the bandwidth. So if I want to increase the SNR, I have a limited range of things that I can do. I can change the power level. I can change the gain. I can't change the backscatter. It is what it is. I can affect the surface area a little bit by changing the system parameters, the pixel area size. The losses, I try to design my radar so that there's little as possible. But the atmosphere is the atmosphere. I can't do anything about that. I can change the range which I'm operating the radar at. And I can try to get the system temperature lower, or if I'm willing to live with less resolution, I can live with less bandwidth. So those are my knobs. And they trade against each other. And that's where the difficulty designs a radar. So it may come as a shock to you, but after your 6 hours today, you're not really ready to go off and design your own radars. So you need a little bit more training to be able to do that.
So it depends on the incident wavelength.
What?
Incident wavelength also it's depending on, right?
Yes, there's a wavelength factor that's in here as well. And that makes sense, right? Because a lot of these things are scaling. The gain is scaling with wavelength, and other things scale with wavelength. And by the way, if you look in books, there are about 20 different ways, equal ways of writing this equation by manipulating these different parameters. This is not the only way to write the radar equation. So I don't want to get a bunch of email from anybody here saying, I saw the radar equation in XYZ book and it was different than what you did. Yes, it may be, but did you check to see if they are equivalent to each other? So yes, there are many different ways of writing this equation.
So increasing the wavelength, what are we using there?
What?
If I increase the wavelength, if I get
So if you increase the wavelength, well, first of all, typically you're choosing your wavelength depending upon what you're trying to measure. So that's not normally a free parameter. There may be a range of wavelengths that you can change within a given band, say at the top of the X band or at the other end. And that has modest effects on things. But this can affect the scattering, but it has a lot of effect on the antenna size that you can get and the amount of gain that you can get. And depending on your wavelength, it affects the type of transmitter technology you're using and therefore how much transmit power you can get. So it's all mixed together. This is what I'm trying to say. The technology is mixed, the scattering, the phenomenology is mixed. And so that's why designing radars for a particular application requires a lot of balancing acts to do that across multiple disciplines. Yes?
Is there any reason the total loss is the multiplication of this component instead of like the summation?
So it's this definition of the way we do the loss. So in dB, it's adding, okay, of course, but we define the losses as a multiplicative term by definition. So and then it becomes additive in the dB domain. So as you say, my loss will be 3 dB plus maybe plus minus 5 dB of atmosphere loss or whatever. It will be multiplicative in the scalar domain and then additive in the dB domain. And then somewhere back over this way.
How much control do you have over your system temperature?
It depends on whether you're airborne or a spaceborne system, what planet you're operating around, and how much you're willing to pay to cool electronics. And that relates to usually your power utilization curve. Again, lots of different things come into play to do that. So sometimes for ground-based systems where it's easy to get power, they can put coolers things, and sometimes they can cool things very, very low and get very low system temperature, like they do for some radars. But for a spaceborne radar or an Earth-based radar, where power may be a lot more of an issue and it's harder to control the environment, then not as much. Okay, so this is how we would normally do this. We give it a dB table. This are the linear units. This is converting to dB. Remember, 10 log 10 of a quantity is how you get to dB. So you take log 10 of 400 times 10. That's what you get. And then in this domain, you're multiplying and dividing things according to that formula. In this domain, you get to add things. And so in this particular case, I get a total SNR of 7.5 dB. Now, things can get more complicated. For instance, if I want to understand, for instance, the accuracy of making an interferometric DEM. That will involve the radar equation, but it involves other things as well, which we'll learn. It involves the interferometric correlation, which depends upon the SNR, which depends upon the radar equation, which depends on all those parameters. But there are other things that are involved as well. And then the gains depend upon the size of the antenna and the wavelength. And then those are the full set of parameters to build an interferometric radar. Well, not the full set, it's still simplified. But again, there are trades. And this is where life gets really annoying. So for instance, if I want to improve my SNR, I can do that by increasing the size of my antenna, which I might increase the azimuth size of my antenna to do. But if I increase the azimuth size of my antenna, then that will increase my azimuth resolution, as we'll learn, as it turns out, which will reduce the number of looks, which will reduce my phase noise. So in one case it's helping, and in the other case it's hurting it at the same time. And I have to balance those things across the full design. And there's lots of different parameters like that in all these various crossing parameters that I have to deal with. So when you ask, some people ask me, well, they always ask me, if I do the X, what will happen to my radar? Well, it's not always that simple to answer. And the reason is this sort of nested complexity of interdependencies that are going on. And so I need to know more oftentimes to be able to answer, quote unquote, the question. So as I already tried to go through, these are some of the implications of the radar equations and, you know, how you increase the SNR and what happens as you do various things. And this is the sort of thing that one has to, you know, keep in mind as you're going through and trying to understand what happens when I do what to a radar. Okay, so that's the radar equation, and that's SNR in a nutshell. Now I want to talk about basically synthetic aperture radars and how we get resolution with a synthetic aperture radar. So I'm going to talk about range resolution and azimuth resolution for them. And we already talked about the phase measurement. I'll just remind you again. Phase is a form of ruler. It basically comes about by measuring distance in terms of wavelength and then multiply by 2 pi to get to radians. Okay, so we already talked about the fact that synthetic aperture radars are going to look to the side, either usually to the left or the right of the platform in order to get their swath. And then their swath will occupy a particular distance on the surface. The radar will transmit an electromagnetic wave, typically in a pulse, that will then have a particular range resolution shown here. And then we will divide the scene into range cells as we propagate across the scene. Remember, the radar will pick a polarization or will transmit multiple polarizations depending on what type of radar it is. The bandwidth, which we'll learn in a moment, determines the resolution of the imagery in the cross-track direction. And then the SAR will use the forward motion of the antenna to develop the azimuth or the along-track resolution. So those are the key things, the key aspects of forming an image. Now, we already went through the slide, so I won't go through it again. Now, one of the things that's involved in producing the azimuth resolution of the radar is the so-called Doppler frequency. How many people have heard of Doppler before?
Yes.
Good. A fair number of you. So the Doppler has to do with the apparent change in the wavelength depending upon whether you're moving toward an object or away from an object. So when suppose I'm flying along at a velocity v and I transmit an electromagnetic wave. So that'll be the purple here. So it'll be of a particular wavelength. What happens then is if I'm flying away from the radar, that the wavelength that I receive will tend to look larger. It will tend to stretch out the wave that I effectively see arriving back at the radar. Whereas if I'm flying toward the radar will seem to be compressed because the peaks will come closer together because I'm moving toward them at the same time. So this change in wavelength is equivalent to a change in frequency. So if I'm thinking of it in terms of sound, it would sound differently. So that's why the pitch, of a train moving towards you or away from you is different. That's the so-called Doppler effect. And it's basically due to a change in the wavelength. Now, that can be done in terms of phase. So frequency is basically the rate of change of phase with respect to time. It's the derivative of phase with respect to time. Everybody's had calculus? Has anybody not had calculus? Okay. And for those who have forgotten, that little curly symbol there is a partial derivative. So this just means change in phase with respect to time. Now phase, remember, is related to the wavelength and the 2 pi. So this is related to the change in range with respect to time, which makes sense then, because this is going to be changing the range to make it larger or smaller relative to the radar. And as it turns out, the rate of change of range with respect to time is the dot product of the look vector into the velocity vector. How many people, does everybody know what a dot product is? Everybody? See some yeses, some no's, and some sleepers. So, so and again, this is in the math review, but basically this means the projection of the velocity onto, how much of the velocity is projected onto the line of sight. That's what that means. And that'll be related then to the cosine of the angle between those two vectors. And so as we fly along, if I have an object there, the line of sight is constantly changing to that point on the ground. And therefore, the Doppler is changing. So the frequency is going to look a little bit different as I image a point on the ground. And what azimuth resolution is going to do is it's basically it's going to take advantage of the fact that that frequency is changing a little bit as I fly through the radar beam. And then I can use that to actually, quote unquote, which to mathematically combine the signals in order to produce the appropriate azimuth resolution. So that's what we do. Now, yes.
So, wave is moving at the speed of light, right?
Yep.
So, until we are observing something at relativistic scales, do we still see a considerable Doppler shift?
Yes, you can. Yeah, it's a measurable Doppler shift. It's still there. It will show up. There is that formula is for non-relativistic case. There's a correction if you're moving at relativistic speeds. But as you remember, I prefaced this class at the very beginning. Nothing that we're doing in this class moves at relativistic speeds. So, but there is another correction term to that formula if you're moving at relativistic speeds. But even if you're not moving at relativistic speeds, their measurements are sensitive enough to tell the difference in the wavelength from the changes that they're, and they will be, in the kilohertz range. So they are megahertz range, depending on the wavelength and stuff. So they're actually measurable by electronic means. Now, there is two things that often get confused, and people get very confused about the two things. So what I just talked about is the change in Doppler because we're moving through a beam. And that's called the phase history. So that was, I'm moving along here. I'm setting a series of pulses. I have a point on the ground here, and the line of sight is changing as I'm flying along. And therefore, the Doppler is changing as I go through the beam. And that means I get a different phase as each point as I move through, and that's called the phase history. And that's all fine and good. There's another term that's showing up that's called the Doppler, and it is related to the Doppler, and that's called the Doppler centroid. And people may have heard about this in their processing. And the Doppler centroid is different than the Doppler associated to the phase history. They're related, but they're different things. The Doppler centroid is the Doppler at the point of maximal gain in the antenna beam, across the beam. So the Doppler centroid refers to the Doppler at the point of peak gain within the antenna pattern. And so this is not changing typically as a function of time. If I'm pointing my beam in a fixed geometry relative to my flight path, the Doppler centroid does not change. So the Doppler history is always changing, it's a function of time. The Doppler centroid is not a function of time, it's related to if I'm pointing forward, backward, or broadside to the radar. And to make that point very, very clear, and to go back to our Doppler formula, and people remembering a little bit about their dot products. So Doppler centroid, suppose I'm flying and I'm pointing my beam perfectly perpendicular to my flight path. It's perfectly perpendicular. What's my Doppler centroid? If you had to guess, you would get this right away. What number would you guess if you just had to guess a number right off the bat?
0.
What? 0. Yeah, that's what I would guess too. If I didn't know anything else, 0, you would be right. And so why is the answer 0? Well, the dot product between two vectors depends upon the angle between them. And if the angle is 90 degrees, cosine of 90 is 0. So this would be 0. And it makes sense because if I'm parting broadside, I'm not getting either closer or I'm not either moving away or moving toward my swath. It's perfectly there. So there's no Doppler shift. So the Doppler is 0. And if my beam is always pointed this way, my Doppler centroid is always 0. So there's no change in anything. But if I look at the Doppler to a fixed point that's in that beam, it is changing because I'm changing my line of sight to it as I go along. So you will see people talk about the Doppler centroid. It's for processing data. It is related to how you process the data and form synthetic aperture imagery. Remember, the Doppler centroid and the phase history are different things. So what determines the azimuth resolution is basically how much Doppler variation. That's the Doppler. That's where the bandwidth comes in the azimuth direction. It's related to the bandwidth that I get in this direction. And so you can differentiate that formula I had on the previous page, and you can end up with this formula right here that tells you what the Doppler bandwidth is. So it's related to the velocity, the size of the antenna, and the angle that you're pointing away from broadside. It's azimuth angle here. And the frequency spectrum that you get, the amount of change in frequency, that's the bandwidth. And this is going to turn out to be related to our azimuth resolution. And what's going to be truly remarkable, which we'll find out in a second, is it will turn out the azimuth resolution will end up in the end only depending upon the antenna size. So it's independent of range, and that's what we get. And that's if we collect the data in the standard SAR imaging geometry. Okay, that's pointing in. You also hear zero Doppler steering. That's when you point to zero Doppler. So pointing broadside to the antenna. I'm going to skip this. Skip this. All right. Yes.
Sorry, I have a question on the slide that you were showing the theta azimuth. Why is the projection on the ground?
Which one? This one?
The next one. What is theta azimuth? Isn't the bandwidth?
Theta azimuth is the angle from broadside to where you're pointing. So I'm flying along this way. Let's say I'm pointing back this way, and I look at the angle between broadside and where I'm pointing on the ground. That's the azimuth angle.
It's not. It's the projection on the ground. It's not with respect to the
It's where the beam is. So this is beam on the ground. This is broadside, perpendicular, and that's theta f. Okay. So the azimuth resolution, we'll come back to that formula a little bit, is related to that bandwidth. But then when it turns out when we work out what happens with that bandwidth, we get something that will depend only on the azimuth antenna length. Range resolution. Well, there's a simple way to separate things in range when you're pulsing the radar. And what do? Let's suppose we have a pulse length of length tau, and I'm going to transmit this thing. It's going to go down here. It's going to reflect off three objects, the orange, the green, and the purple object. If they look different to you, I'm colorblind. I apologize, but to me, that's orange, green, and purple. All right. And so this as a distance rho to the first guy right here. And we do this. Now, as I go along, I'm going to move along. My pulse is going to go along. And eventually, I'm going to be getting returns, if this is fat enough, from both the orange and the green line at the same time. So if I'm getting returns back from both at the same time, I'm not going to be able to tell them apart, right? They're going to blur together. Can't see them anymore. And then, because the purple line separated far enough away, it's fatter than the pulse, it will eventually show up, and it will show up differently. So these two guys, I won't be able to tell apart, but I'll be able to tell these two guys from that guy. Does that make sense to everybody?
Can you repeat?
Sorry?
Just repeat it.
Okay. I have three objects. Got that? And they're separated by different distances. And I'm transmitting a pulse here. So for every point in here, I'm going to get something. Every time I move through, hit an object, it's going to give me something back for this entire duration. So as this propagates down here, as soon as it hits the orange guy, I start getting a signal back until I pass all the way through the black guy, okay? But since the green guy and the orange guy are smaller in distance than the black guy, I'll eventually be getting signal back from both of them at the same time, right here. So I can't tell them apart, they blur together. But since the purple guy is separated from the green guy by more than the black length, I will eventually get through both of these two guys completely. And then there'll be a little bit of time separation, and then I'll see the purple guy. So I'll be able to separate the purple from the green and the orange, but not the green from the orange. Does that make sense? So what does this mean? If I want to have finer range resolution, what do I do? What? Narrow my pulse. Narrow the pulse. I make this smaller. Smaller and smaller. Okay, that sounds perfectly good. Well, why can't I just make tau as small as I want? What might prevent me from making this smaller and smaller?
Range resolution.
What?
Range resolution will get lower.
Oh, I've heard a couple of answers, but nothing that's not quite right. So let's do what I'm a mathematician, so I always take limits to understand things.
Number of reflections from one object would be lesser.
What?
1 point will be mapped for less number of times if I'm shortening my pulse.
That's basically the right idea. So what she's getting at, if I take the limit, as I was going to say, is tau goes to 0, what happens if I make a 0 length pulse? Do I get anything back? No. So what happens is the smaller I make the pulse, if I keep the amplitude the same, the amount of signal I'm going to give out gets smaller and smaller. So you say, no problem, Scott. I'm just going to transmit a narrow pulse with higher power. But now you run into electronics problems. There's a limit to how much you can do that. So if I want to get the right amount of signal to noise, I'd rather have a fat pulse because I can get more and more energy coming back from that for a given amount of power. So I want to have a wider pulse. But at the same time then, I have a problem because if I want finer resolution, I want a narrower pulse. So, being smart guys that we have in this room, you guys tell me, what can I do about this? How do I fix this little problem? What do I need to do? First of all, what would help me solve this problem? Even if you don't know how to do it, what do you think in principle would help you solve this problem?
Increase the bandwidth.
I haven't even talked about bandwidth yet. Bandwidth's not even here yet. It's more basic.
Multiple pulses?
What?
Multiple pulses?
Well, how will multiple pulses help? I just have more confusion out there.
Choose target.
What?
Choose target. Like one.
I don't get to choose my targets. My targets are out there on the ground. Are you going to go rearrange the trees in the forest for me? I have a lot of work for you. You're employed for life. Yes?
Increase the size of the antenna
How does that help?
so that we can able to measure the smaller with a higher resolution.
Mm-mm. The antenna size affects the signal strength, but not the resolution. It affects the size of the footprint, but the footprint isn't the resolution either, except in I want a real beam radar, not a synthetic aperture radar. So let me try. I'll try to help you out. What's the real problem when I look at tau? There. In my image right there, tau is one color, right? It's all black. Every part of the pulse looks the same as every other part of the pulse, right? They all look the same. Suppose I changed the black guy so that part of it was black and part of it was gray. Would that help me? And I could tell the difference between black and gray. I don't see, everybody should be saying, oh yeah, God, that's a great idea. Why are you not saying that's a great idea? So let's suppose I colored the first part black and the second part gray, and I can tell the difference between black and gray. Well, if I can do that, as this guy goes along, first of all, I would hit here, and I hit the gray guy first, and then if the gray guy was narrow enough, before I got to the green guy, then if it changed color, I would now be able to separate the orange from the green because I could tell the difference between black and gray. Because I get effectively a narrower pulse, right? By changing that. So the key thing is, what I need to do is the problem is I can't tell the difference about where I'm at in my pulse. It all looks the same. So what I want to do is I want to make things look different across my pulse. Okay, so now I've solved the problem for you.
But when the black pulse will map the orange object and the white pulse will again map the orange object, how to get the resultant out of?
Because this means that basically I see what I get from the black guy and the gray guy or the white guy, whatever you wanted to call it. They'll be a little bit different. So I can now separate them. So I get basically two images with finer resolution. And then if I can combine them together to get the better power, then I get the best of both worlds. I get more power and more resolution at the same time. So now that I've told you the basic answer is to make things look differently here, what can I do to make things look differently?
Modulate it.
Polarization is one possibility. Turns out that's not a really good answer for this particular application, although people do that in other applications, communications. What else? What else can you change about an electromagnetic wave?
Frequency.
Frequency or
Wavelength or frequency. So if I change the frequency, bandwidth, so if I change the frequency across here, the wavelength or the frequency will be different across here, and that's bandwidth. The change in frequency across the pulse will be the bandwidth, which will turn out to be related to the range resolution. So that's the answer. And there are other ways to do it. There's another thing called phase coding, where I change the phase in little chunks across here. That's called phase encoding, and that's another way to improve the resolution. So whatever I can do basically to change or be able to distinguish the different parts of the pulse allows me to make it narrower. And then as long as I can combine them together to get all the power back in the end, I get both the improved resolution and the improved power. And that's how we solve that problem.
I have a question.
Yes.
So do we have like a spectrum of different frequencies, or do we just fix two frequencies and send them?
No, that won't help. So you need to have a range of them. And so that's what I show here. Basically, we want to change the color in such a way that we have enough changes in color to represent the total resolution we want. And typically, we just change it continuously across there. And that's called a chirp. So if I change the frequency continuously across my pulse length, that's called a chirp. And then the range resolution is C over 2B. And that 2 again comes from the two-way going. And C is the speed of light. So this is my range resolution. And this, by the way, is an important formula to know for the quiz, maybe. So maybe. All right. So what you really need to know is that the range is inversely proportional to the bandwidth. So the bigger the bandwidth, the finer the range that you get. Okay. And it makes sense. Bigger bandwidth means more information, which means more range. This is the other way to remember it. Just remember your Wi-Fi. I know you're all addicted to that, so easy to remember. Now, I'm not going to go into the math. So here's a typical example. So if I have 20 megahertz of bandwidth, 20 times 10 to the 6, 20 megahertz, that would be 7.5 meters of range resolution. Okay. And that's a typical range resolution of an Earth-based imaging radar. They go up to 300 megahertz or even higher for fancier systems. But there you go. I'm going to skip all the math. This is showing you how to relate it to bandwidth and back to the sinks again going through the Fourier transforms of things. But that's more math than we have time for before lunch, so we'll skip that. And the process, for those who know a little bit about signal processing, of extracting this, it's basically a convolutional match filter is what we do to do what's called range compression. So we basically have our waveform, that is our filter, that forms our match filter. We do the convolution, and that allows us to improve our resolution and range. And again, I won't go through the math because it takes a little bit of time, and not everybody is probably up for it just before lunch anyway. So, and as I said, the standard way of doing this is what's called a chirp, which is where we change the frequency linearly across range. And chirp comes from the fact that birds change their frequency when they chirp, blah, 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 from a bird. So, excuse me, I have no musical talent whatsoever. So anyway, so you have a chirp here. So we have that. So the pulse length is tau. So from my is tau to tau over 2. We would change the frequency from here to here. That change in frequency over the pulse is called the band.
Is it in the decibel levels or is it linear?
This is truly linear. We don't measure frequencies in decibels.
Oh.
Not everything gets measured in decibels. Power levels are measured in decibels, a few other things, but not frequencies. Okay, and so that goes through the math of doing it, and then the sync shows up again. So that's the other thing to note. So the other thing that you would like, of course, is when I'm doing the range compression, or this technique for getting finer resolution, what I would like, of course, is for all the energy of my object to only show up in the pixel where it is. Alas, you don't get that. What happens is the energy spreads out over all of space. Basically, it spreads out across there. So you get the most energy where you want it, but then you get some energy where you don't. And so that's called the range side lobes. And so again, you get energy going in places that you don't want. And again, it's because this is related to a Fourier transform. So because you can't have an infinitely long pulse, you can't localize the energy all to one place in space. And so it spills out. And this happens in both range and azimuth. And unfortunately, it's the way the world is, and it can complicate looking at imagery and understanding it. But that's something we have to deal with. And again, we can do windowing to try to reduce those side lobes at the expense of range resolution. Nothing is for free. Okay. So azimuth resolution from synthetic aperture radars, we've talked about that before. And what we learned is, that the synthetic aperture will basically be the amount of time as we walk through an image, a point in the beam. So from the time we go in to the time we go out. And so the length of my illumination will be my range times my bandwidth, which gives me this here. And then if you want to work out what the spatial resolution is, it'll be lambda times the beam width associated to my synthetic aperture length. And therefore, you see that my synthetic aperture length will be the azimuth resolution divided by 2, because the range will cancel out from those two formulas there. So if you plug this formula into here, so you're multiplying by the beam width associated with synthetic aperture, which is lambda over the size of your antenna, times the range, plug that formula in, you get the azimuth resolution of 2. So the azimuth resolution of a synthetic aperture radar is the physical size of the azimuth antenna divided by 2. Notice it too is independent of range. So the range resolution formula was dependent only on the bandwidth, and the azimuth resolution only depends upon the size of the antenna. And both are independent of range. So this is a remarkable, remarkable result. So it tells you can make very long range synthetic aperture images provided you have the right antenna and the right amount of transmit power, and you can get very good resolution that depends on these quantities. And that's basically, how I made high resolution images of the moon from the Earth, even though it was very, very, very far away. I'm not going to go into this too much. In fact, I'm not going to hardly go into it at all for this basic course. But I do need to bring this up because you'll hear about this. So, as I mentioned before, we have a pulse system where you transmit a series of pulses. We call that, the frequency that we transmit them is called the PRF, the pulse repetition frequency. And the pulse repetition frequency is very, very important. It relates to how we're sampling in the long track direction, and it also relates to how much room we have between one pulse and the other. And that determines how much of the swath width that we can get. So the PRF affects the size of the swath, and it affects the resolution that we can get. And if we're trying to get our full resolution of L/2, then it turns out we get a particular swath width. And this extra energy that's going to be is constantly coming in from all other places and folds in. Those are called range and azimuth ambiguities, and it's related to the way we sample the data in both range and azimuth. And we have to arrange our antenna size appropriately depending upon the swath width we want and how much resolution we want to get. So for the finer resolution, typically that means for a given size antenna that, we're going to get a narrower swath. We can change the dimensions of the antenna to keep the same gain that we're getting, same signal to noise, but we end up changing exchanging resolution for swath width. So it's a little bit more detail than I want to go into, but I wanted you to know that there's other energy that's coming from other places in the scene that's related to the PRF, both in the range direction and the azimuth direction. It's called range and azimuth ambiguity. And we have to have the right PRF in order to keep those ambiguities at the right level. If we do it too low or too high, we can have a problem in either range or in azimuth. And of course, they go in opposite directions because it would be too nice if they worked in the same direction. The laws of physics just won't allow that. So what we really want is higher PRFs in azimuth and lower PRFs in range. And there is the yin and the yang again of radar design where we have to deal with the competing aspects of getting both of those things at the same time. Okay, so raw data. So when we're going to form a synthetic aperture image, we're going to collect data and we're going to record it. If I look at raw data that's recorded from radar, it looks like noise. It looks like, an old TV. You guys don't know what those look like, but an old TV, basically, if the image didn't form right, it would just look like a bunch of brown dots all over the place. It would look like, and that's what radar imagery looks like. It doesn't look like anything. You can't tell, you can't recognize a thing from it. It looks like complete salt and pepper everywhere. So until you do sophisticated mathematical processing to the data, it's not an image. So you have to do that range compression step and that azimuth compression step before something will actually look like an image in the data. So this is what happens with range compression. You start to separate things in range, and then you get azimuth compression afterwards. Now, I will only mention this briefly. There are different ways to collect data, and that you'll read about, and the different SAR systems that are actually flying employ a number of these and other data collection concepts, which are not on this slide. So the standard case in which I have been describing, and which the azimuth over 2 formula applies, is when I'm transmitting a continuous stream of pulses and collecting the data. So I'm flying along and I just pulse happily as I'm going along. That's called standard strip mode processing, the AT. But that's not the only way to collect data. Another way to collect data is the so-called scan, SAR, or burst mode. And in that case, I transmit a series of pulses. My radar takes a break, goes to sleep, does whatever, and I transmit another series of pulses. The radar goes to sleep and transmit another series of pulses. Why would I do that?
Save energy.
Save power might be one, but that's not the primary reason.
Receive.
Repetition of
What?
repetition of acquisition from same point.
Not really, no.
They're used for larger areas.
That's one reason to do it. So the scan-SAR thing is what she was referring to, and that's the idea is, okay, suppose I point my antenna when I'm transmitting here to a particular swath. And let's suppose that I can change my antenna position during this part to look at a different area over here. And then I ping pong between the two. So now for a given sized antenna, I'm able to get a wider swath with good SNR for those two areas. Nothing's for free. What did I pay? Sounds too good to be true. So I must have paid for something. So what am I paying? Resolution where?
Noise.
Range or an azimuth? Azimuth. Because remember, the formula that I derived, it says that my resolution in this case of the antenna 2 means I'm basically integrating going from one edge of the beam to the other. If I don't do that, if I only go through a portion of the beam, I only get a portion of the azimuth resolution. So in the burst mode or the scan-SAR mode, I'm going to lose azimuth resolution. So I pay in azimuth resolution. So I gain in swath, in the ScanSAR mode, but I lose in azimuth resolution. What if I don't want to collect the other swath? Do I get a benefit in that case, or do I just get a fine less resolution but no benefit at all?
Can you repeat the question?
Yes. So suppose I don't want to get a wider swath. I'm not doing ScanSAR. But I'm going to do burst mode. Is there no advantage to doing burst mode? Do I just lose? I don't get as good azimuth resolution and I don't gain anything?
Be less data produced.
Less data produced, that's right. So data can sometimes be a big deal, particularly for planetary radars. All that data has to be transmitted back to the Earth. Radars collect a crap load of data. So they're operating and collecting samples at a very, very high rate. So if I collect less pulses worth of data, I collect less data and I have to transmit less data back to the Earth or back to a processing center. So I save on data rate. So in these cases here, these modes are chosen because they bias something that I need and I'm willing to give up something, namely azimuth resolution, in order to achieve that. In some cases, I want even finer resolution. I want better than the azimuth resolution over 2. And I can do that. And how do I do that? Well, instead of just pointing my antenna in a fixed direction, suppose I stare at the same spot on the ground. So let's suppose I'm interested in that point. So as I fly along, I continually point to that same point on the ground. Now my integration time, the number of pulses I get is getting longer and longer as I do that. And that will improve my azimuth resolution. So I also do not want to hear people coming back. Scott said the azimuth resolution was the antenna length over 2, and you can't. How come you can do better than that? You can do better than that if you collect the data in spotlight mode. All right. What do I lose? What's my penalty? What? No, not necessarily, but something.
You don't get
You're close to it.
continuity.
I don't get coverage. I lose coverage. If I'm going to stare here, that means I'm not looking there and I'm not looking there. So I'm getting gaps in the data. I lose coverage. So I get azimuth resolution at the expense of coverage. Again, nothing's for free. I have to pay for it to get it. And there's other modes called, like the TOPS mode is another mode that you might read about that radars use. It's a form of ScanSAR that's out there that has some advantages, and I won't go into that. So there are ways of collecting data, and how you collect the data, you're basically making a trade for one thing versus another that you're trying to optimize. So for SRTM, for instance, we wanted to have a swath width of 200 and so kilometers. And the reason we wanted that is because we were going to fly this radar on the shuttle, and the shuttle could only be in orbit for 10 days. And we wanted to map the entire world. And so if you work out the number of orbits that the shuttle flies in 10 days, divide that, turned out that we needed a very wide swath, a swath of about 250 kilometers. But it turned out that the swath that the radar could collect was only about 50 kilometers. So we went to a ScanSAR mode, and that still wasn't good enough. So we did one at H polarization and one at V polarization. And that's how we got the full swath width that we needed. So again, you can mix and match these ideas in order to try to get what you need. I hate burst mode, by the way. And this program certainly made me even more annoyed with it. So, but anyway, it worked. And we were able to make a very good topographic map of the Earth using that technique. So this is a strip map mode, and this is a ScanSAR mode that you can see. And this is very hard to see, particularly with all the lighting on. But maybe you can see some of this banding that's showing up here. This is one of the other disadvantages of the ScanSAR mode, is you get this scalloping effect. So the radiometric compensation, compensating for the antenna pattern, to get rid of that becomes more complicated. So there's other complications as well. Okay. I'm probably going to skip this. Let's see, how are we doing? Oh, we're a little bit over. Let's skip this. And let's stop here because it is lunchtime and I don't want to cheat you out of your lunch. So we'll come back here. We'll do a little bit more on radar before we switch over to interferometry. So Everybody have a really good lunch. Since I stole 7 minutes, I will give you back 7 minutes. I'll be back here by, say, 1:10. I'm giving you an extra 3 minutes. Don't be late.